So in this video we're going to go over level curves or contour maps, and we're going to do this two ways. So it's going to be a lengthy video, and I know you're going to hate that, but I'm going to do it first by hand, and then I'm going to do it in GeoGebra. And in GeoGebra I'm going to try to really drive home conceptually what's going on. So a contour map, what you do is you pick values for your function, for z, right? Z equals our function f of xy. And we pick specific values of z and we set them equal to the function, and then we look at what the projection of the function into the xy plane would look like, and we usually give the values for z the name c. So for example, I'm going to do a level curve or contour plot map for this very mechanically by picking c equal to 0, 1, 2, and 3. I'm going to do this by hand. And then we're going to move into GeoGebra and actually look in 3 space at what we're actually doing, so that the concept part of it is driven home, which is and the conceptual part is the most important part. So the way that I would do this just mechanically is I would set each of these numbers. I'd replace the f of xy with each of these numbers. So for example, I would go 3 equals minus x squared plus y, and then I probably would solve it for y, and if I did that I would get y equals x squared plus 3. And then what you do is you graph this. This is taking a graph that was in the xyz system and moving it into a graph that lives in the xy plane, and I would graph it in the xy plane. And in the xy plane, this is just a parabola that's been shifted up 3 units on the y-axis. So this is the y-axis, this is the x-axis, and then you label this. You say, hey, this is c equals 3. So instead of plotting the point in 3-dimensional space, you're just saying at a height of 3 units out here, I have a parabola. And then you do the same thing for the 2, the 1, and the 0. So I would go 2 equal, I would replace f of xy with 2, and I would go 2 equals negative x squared plus y. Solve it for y, get y equal x squared plus 2, and graph that parabola. That's a parabola shifted up 2 units in the xy plane. It's going to be a horrible looking graph, which is why I usually use the computer algebra system to do this. So you label it with the value that you substituted in for the function, c equals 2. And then we do 1, so we do 1 equals minus x squared plus y. Solve it for y, we get y equals x squared plus 1, and that's just a parabola shifted up 1 unit. So that's for c equal to 1, and then we would do it for 0. 0 equals minus x squared plus y. Solve for y, we get y equals x squared, which is just a parabola at the origin. And then we would label that c equals 0. It's a horrible picture, but these are the level curves for the function, or the contour, a contour map for the function. I could pick infinitely many values for c. Usually you do enough values so you get a good mental picture of what's going on. Let's look at the same thing done in GeoGebra. So I'm going to escape out of PowerPoint. I'm going to go ahead and keep that. So f of xy equals negative x squared plus y is a 3-dimensional graph, and here's the picture of it right here. So I've got it in graphed in GeoGebra. And then what we did to make the level curves is we picked values for c. So in particular we picked c equal to 0. That's not a very large point. Let's do thick point. We did c equal to 3, 2, 1, and 0. We pick those values of c. Well, when we set the function equal to f of xy, when we set it equal to 3, and we set 3 equal to the minus x squared plus y, really what we're doing is intersecting this surface with the plane z equals 3. So if I step down into my input bar, let's see, where's my selection tool? So if I step down into my input bar, I can type in z equals 3, and if I do that right here, I get a plane at a height of 3 units above the xy plane. This is the plane z equal 3. And what we want to do is intersect the surface with the plane z equal to 3. So when I do that intersection, I get a parabola that's 3 units above the xy plane. And what the level curve is the shadow of this parabola cast down into the xy plane. So when I set 3 equal to negative x squared y, and when we solved it for y, we got y equals x squared plus 3. We got this parabola here in the xy plane, which is just, if you look over here, it's just the shadow of the intersection of the plane z equal 3 with the surface minus x squared plus y. We cast that shadow down into the xy plane. So we're really doing a 3-dimensional representation of our function in the xy plane. And then of course we need to label this line with as c equal 3. So in GeoGebra what I would do is go into the ABC window here, and this is select a position to make text, and I'd click and I would just type c equal 3, and I would probably turn on my LaTeX formatting so that I get a nice mathy looking guy, and I'll move him somewhere in the xy plane so that I think he's going to be out of the way for the future. And then what we did is we did the same thing again, but then we set the function equal to 2. So we did 2 equals minus x squared plus y. We solved it for y. We got y equals x squared plus 2 when we did that, and we graphed that. But what is really happening is, I'm going to turn these guys off. What's really happening when we do that is we're doing the plane z equal 2, which is right here, and then we're intersecting that plane with the graph, and when we do that we get a parabola, and then we cast the shadow of that parabola down into the xy plane. So y equals x squared plus 2 is the intersection of our surface with the plane z equal to 2. So we get a parabola shadow cast down from the intersection here into the xy plane. So there's those shadows in the xy plane right there. And then you've got to label him. So text, he's going to be c equal to 2. And we'll turn on the LaTeX formatting and move him somewhere where we hope he might be out of the way when we start to do the next one. So we just keep going through and doing that. Okay, now we'll turn those two off. To get the next one, we set c equal to 1. So we just simply, on the PowerPoint, replaced f of xy with 1, and we said 1 equals negative x squared plus y. And then we solved it for y. We got y equals x squared plus 1, which is a parabola shifted up 1. But what we want to recognize is that's the same as creating the plane z equal 1 right here. Let me get my rotator. Cancel that. Cancel. Cancel. I've got a road. There we go. So we type in the plane z equal 1, which is in light blue here. It intersects with the surface, and then we get an intersection that's a unit above the xy plane, and we cast the shadow of that intersection down into the xy plane by graphing y equals x squared plus 1 in the xy plane. So there he is right there. And then we label him. We say, hey, you're what I got when c was equal to 1, when I set z equal to 1. Turn on LaTeX formatting to make it mathy looking, and slide him over somewhere where we hope he's going to be out of the way. And so with 0, it was the same song and dance. So we turn off the plane z equal 1 and the intersections. For z equals 0, it was simply a matter of replacing the function with 0. So instead of f of xy equals negative x squared plus y, it becomes 0 equals negative x squared plus y. We solved it for y. We get y equals x squared, which is just in the xy plane is just that parabola at the origin. Here he is, but he is just the intersection. Turn on my rotator. He is just the intersection of the plane z equals 0 with the surface. But the plane z equals 0 is the xy plane. So what we get is a bunch of shadows being cast. When we're setting c equal to a constant, we're doing planes parallel to the xy plane. We're doing planes that are parallel to the xy plane. We're finding the intersection of those of the plane with the surface, and then that intersection is above the xy plane, but then we cast that shadow down into the xy plane, and then those are our level curves. So it's a 2D representation of three-dimensional space, and you see this in lots of places in the real world. So for example, whoops, I was sure I wanted to close it. If you were to for example, look at a contour map, so contour maps happen when you take and set lines of equal elevation. You set elevations to certain constants, and then you cast the shadow of those lines of equal elevation down into the xy plane. And so when you're reading maps, that's what you're looking at, is a contour map, or level curves of your uneven surface being cast onto an xy plane. They do this with temperature gradients, air pressure gradients. There's all kinds of contour maps that exist in the real world. So this is kind of our first introduction to that.